are we online now? Got nobody? Got Andrew. No Dan, no nobody? All right, these are going to be homework problems. So. Okay. So perturbation method. So if you recall, the motivation here is that I said there were different types of PDEs and PDE methods. And I listed some of them, and we've done 2, and this is the last one we're going to do. So the first one we did was a combination of variables, and then we did separation of variables, and separation of variables turned out to be pretty general, and we derived a different way to write it down, which we called the method of eigenfunction expansion, where if you know what the eigenfunctions are, you can just write a series and plug that in and skip a bunch of steps in the other method, and that one works pretty well. We have to know the eigenfunctions, so you can either look those up in the table or you have to solve the eigenvalue problem for yourself. And those methods are great for linear systems in which we have either a semi-infinite domain or a bounded domain. I said there were other PDE methods for doing things like completely unbounded domains, or when you have inhomogeneous boundaries, et cetera, et cetera. And we don't have time to do all those. Unfortunately, that would be really fun, but we don't have time. So instead, I said we're going to do one that's really important because it has to do with boundary layers, which is a key piece of transport. And so this is a really important one to do. And this is perturbation method. And the thing that perturbation methods do that you can't do by other methods is that you can solve nonlinear systems, or at least you can start to solve it. You can get approximations to that. And they're foundation behind tons of theories that you see everywhere all the time. Once you learn this, you see it all over the place. And it's all over our book. They don't go through it formally, but it's all over the book. You'll see it everywhere. So, so what I talked about last time then was I said, well, there's these asymptotic expansions. And essentially what you're doing here, right, is you're writing a function as a series that's a power series at some small parameter epsilon. Okay. And essentially what you're going to do is if this parameter is small, then at n equals 0, you have some order 0 function, and then you have some order 1 function, order 2 function, etc. And you build up a set of approximations for each of these functions to solve the differential equation of interest. Okay, and then I did an example which I called the regular perturbation problem. And so I hope if you're not remembering that, I hope you can go back and watch that video again. So that was a regular problem. And we're going to do a second example, which is going to be an example of a singular perturbation problem. So the regular perturbation problem, I think, is pretty straightforward. It's a little tedious, but it's pretty straightforward. There's some wrinkles to singular perturbation problem. So that's your singular. Okay, so let's just start with the example. It looks a lot like our example from B. In a packed bed with flow. So the one that we had in part B was reaction in a packed bed, but no flow. So we've got some tube here filled with packing particles. Okay, I'm not going to draw all of them. And I'm going to call this Z equals 0, this Z equals L. And I'm going to do something a little different compared to the one I did on Wednesday. I'm going to put flow, and flow is going to go from right to left, which is a little funky, but it makes the math a little easier, so that's why we do it. And I'm going to call the concentration over here, concentration of A is 0. And I'm going to call the concentration over here equal to some CA naught, some value. Okay, and those are constant concentration conditions. So I might have flow out here that's flushing this on both sides, flushing. Okay. And these particles in the packed bed, so this is packed bed. Okay. These particles are decorated with some kind of catalyst. And there's a reaction of A going to B. So two A's couple up into the B. So that means we get a rate law of minus K Ca squared. Okay. And the other thing we're going to assume is that the flow is uniform. So this is uniform flow. So this would be, this is plug flow. Okay, so this is a plug flow reactor. And what we're going to look at is we're going to derive the concentration distribution in this plug flow reactor, right? We're going to, and it's nonlinear. It's going to be nonlinear because we've got a nonlinear rate law here. So we can't solve that using, say, separation of variables because of that term. Okay, so questions about the setup. Does this make sense? Yes.
Is there a reason you want to
It makes the math a little easier at some steps in the problem that aren't obvious. All right. So it doesn't really matter. You could do it the other way, but then you have to do some tricky things by changing your variables to be 1 minus something. And when you take some limits, it's a little it's easy to get confused. So by that I mean I tried it that way too, and I got confused. I just decided I was going to go the way that more problem. Okay, so let's write down our equation. So we're going to write down a species mass balance, right? So this is pre-first test stuff. So we should be able to do this pretty quick. So we have dCA T is equal to grad squared Ca. I forgot the diffusion coefficient minus K Ca squared. Okay, so that's our transport equation. And we have boundary conditions Ca at, let's see, I don't know, we're going to put time, we're going to put space 0 is equal to 0. Ca at time and L is equal to Ca naught. And there's some initial condition I'm not going to care about. So we'll call that Ca, I don't know, tilde function. Okay, so the first thing we're going to do is simplify this a little bit for the problem of interest. So here we're going to say that we're going to do this as 1D, right? So Z direction only. And I'm going to assume steady state. Okay, and so I'm going to get dCA, or excuse me, I'm going to write it out and then I'll assume steady state. So let me do 1D first. dCA dt plus VZ dTA Z is equal to diffusion coefficient, second derivative of Ca with respect to Z minus K Ca squared. Okay, so that's one dimension. And then I can do this guy, and I get steady state. And I know what VZ is. That's minus U, right? U's flowing back that way. And I'll rearrange. So I'll put this guy up front, and everything becomes a total derivative because now I'm only down to Z derivatives. So I have D for the diffusivity, dCA, dZ squared. And then I'm going to move that over to that side. So I'll get a plus U. Oh, full derivative. dCA, Z plus KCA squared. No, I like minus KCA squared. Okay. So the next thing we want to do is non-dimensionalize this guy. So this should be there. Okay, so we're gonna make this thing dimensionless. So I'm gonna, let's see, make dimensionals. This will be really important, as we'll see in a second. So we're going to define the variable phi is equal to CA divided by CA naught. And I'm going to define X equal to Z divided by L. Okay, so tell me to take 2 minutes and do that non-dimensionalization on your paper. And maybe I'll wait a minute and then I'll start. Let's see if we can do it. Okay. I win. I won. Maybe not. Mark's sitting there playing on his phone. Looking something up. See, I got second place. Okay. What are those dimensionless groups? Do you know what those are? Do you remember what those are?
Is the first one the Peckel number?
Peckel number, that's right. Yeah. Peckel number. Yep.
Should that be DCA not squared over L squared on the very first step at the top of that? When we substitute in
CA naught squared.
should it be squared or no?
No. Okay. If I take a derivative, right? That derivative has units of, I think about it, it has like a slope. So I'll have a change in F, I change in X. Right? If I have a second derivative, still have something on top divided by something squared on the bottom. But this doesn't square that part of the top. Okay, about taking. Good question. Hey, who knows what this one is? The dom coin of it. Yeah, that's right. Okay. So these are the same two, or this one is the same one that was in the problem last week. Okay. All right, so we can write that down now. So we'll put d2 d squared plus Peckel number d3 x minus the Dom color number v squared equals 0. Sweet, we're down to two parameters. Okay, two-dimensional groups. And we're going to do one more rearrangement here. Well, I'm going to just put up this. P at 0 is equal to 0. So if I look over here, when I'm at z equals 0, my concentration is 0. So that's phi is Ca divided by C naught. And then I have phi at 1 is equal to 1. So I'm over here at z equals L, which is x equals 1. Okay, so this is the problem that we're going to solve. Okay, so I want to think about this for a second. So we are going to consider the case where we have Dom color number much greater than 1, but the Peclet divided by the Dom color ratio is order 1. Order 1 meaning something between like 0.1 and 10. Okay, so in that case, I want you to think about for a second, what do you think the plot's going to look like? Think about what we're going to expect out. If I plot the concentration here, plot Z here, and 0, L. What is my solution going to look like when I have no flow and no reaction? We should know that one just by looking at it.
It's just going to be the second derivative equals 0.
Right. So what does that profile look like?
It should be a parabola.
Not a parabola because it equals 0.
Oh, sorry, it should be a line.
It should be a line. That's right. Okay, so that's the case when the Peclet number equals the Dom color number equals 0. Okay, so now think about it. So what happens if I have flow? So if I've got this concentration profile that's linear. Now I add flow. So flow is in the Peclet number, right? That's the only place where it appears. There's the U right there. So when I have a finite Peclet number, how's the profile going to change? What do you think? Is it going to have a huge spike in it? Is it going to go up? Is it going to go down? What do you think?
Would it then look a little bit like a parabola, like I think it was Zach was saying?
So concave up or concave down?
Concave up.
You're saying something like this?
Yeah, something like that.
You gotta still connect to those 2 points, right? So that is not what's going to happen. Okay. So why? So you're thinking mathematically. So think physically a little bit. If I have a tube and I start flowing, I put pressure on it and I start pushing, water through, and there's some solute. Is it going to be more linear or less than linear? It's going to be more than linear, right? Like it's going to.
Is it more linear or less linear? Not more than linear.
I see. So it's going to go over like this. Does that make sense? So there's some kind of momentum, right? Pushing that in. There's diffusion here, but there's extra convection that's carrying it from the side where it's high concentration into the system, right? So this is the case here where Peclet is greater than 0, but the Dom color number is 0. Okay. Yes.
How does it go to zero? If there's no reaction?
It goes to zero the same way that it has to if it's diffusing. There's well-mixed system out here, right, that's at zero concentration. So I have some convection. As soon as there's a little bit, it sweeps it away. Otherwise, like that's how I hold concentrations constant, right? Is that confusing? I mean, we talked about this, if you remember, we talked about we have a mass transfer coefficient. And we said if the mass transfer coefficient is really low, we can get essentially a constant flux. And if the mass transfer coefficient is really high, we can get essentially a constant concentration. So it's like HT minus T infinity. It's a K, KCA minus A. Right, and that was equal to a flux. And when this number is really, really high, it's essentially making those two things equal to each other. Does that make sense? No, does that make sense?
Just need to think about it. So it's in your diffusion.
Well, I mean, these boundary conditions here, right? It doesn't matter what's happening inside the tube. They're enforced by the stuff happening outside the tube. So I've got some well-mixed thing out here before it gets pushed in, some well-mixed thing out here after it gets pulled out.
So and it's just if there's no reaction, then I would think it would be mostly just the concentration on the right until it gets to the end and then it goes down to the concentration of the outside.
Yeah, so it depends on how much convection there is relative to diffusion, right? That's what the Peclet number is. So if the Peclet number is really, really high, it's going to be more like this, or like you're saying, right? If the Peclet number goes to zero, it'll be on that line.
Okay.
That makes sense? Yeah, that's good thinking. Okay. So what happens with the Domkohler number then? What's the Domkohler number doing? It's like pulling teeth today. I'm not gonna get you.
So if the Peclet number has it above the line, then Dunkler is probably going to have it below because it's consuming concentration.
Oh, yeah, it's consuming, right? So it's going to have to go like this. So this one will be the Domkohler number greater than zero and the Peclet number zero, right? So if I've got reactions, as soon as I get exposed to there, right? I've got extra stuff pulling Ca out of solution, right? Turning it into B. So I'm going to have less concentration than I would with just pure diffusion. Okay, so then we think about that. So what's going to happen when we have both Peclet number and a Domkohler number? So in that case, we're going to get something it's kind of like in between. Going to kind of do this kind of thing. Okay, so we're going to have something where we've got reaction at the beginning, okay, and then there's flow pushing it. So we're going to get some kind of profile that looks kind of like that. That makes sense? Okay. So
Dr. Tree, did you say that the one that crosses the linear line is when they're both non-zero?
yeah, yeah.
Okay. Would it ever flip directions? Probably not, right? Because the Donkler will react quickly at the start and then
Yeah. High concentration, at the highest concentration of A, it's going to react the fastest.
Awesome. Yeah.
Okay, so with that sort of physical idea, let's think about the math a little bit then. So if the dom color number is much bigger than 1, and perturbation problems, do I want big numbers or small numbers? Small numbers. Did nobody watch the lecture? Is that what's going on? Or did we just not understand it because I talk so fast? Anyway. Or are we just so tired and it's Friday and we don't want to do it? Okay, we want small numbers, right? So if the dom color number is big, then I want to divide by the dom color number so I get small numbers. So I'm going to divide every term by dom color. So I'm going to have d2phi dx squared with a 1 over dom color in front of it, plus, and here I have Heckley divided by dom color number, and this one's what? This one's just a single derivative, d3 dx, and then the last one should just have nothing. I think I missed a sign. Okay. And so we used a variable when we had small numbers. We said we used epsilon when we had something small. So I'm going to call the inverse dom color number epsilon. And then so I don't have to carry around epsilons here, but I said I was going to make the ratio of the Heckley number and the dom color number equal to 1 or equal to something close to 1. I'm going to define alpha equal to dom color divided by Heckley number. And I'm going to get the following: epsilon d2 phi dx squared plus 1 over alpha d phi x minus phi squared equals 0. And now we're basically just pure math at this point, right? We've even removed the dimensionless numbers to make us think we're doing anything other than just a math problem. I mean, the dimensionless numbers are still there, but this is what this is so alpha, this is some number. Okay, it's going to be dictated by the problem. It's going to be order 1. Okay, and epsilon, some really small number. Okay, so who remembers what we did when we did the regular perturbation problem? How do we start? What is it that we do to start these problems? Remember? Nothing? I write a series, exactly. So I write phi is equal to some series n equals 0 to the n, epsilon to the n, phi sub n. So I'm going to write e to the 0, phi 0 plus e to the 1, phi 1 plus, that's all I'm going to do. Can I keep up to order 1? I call this order epsilon. So I've got some series that has terms of order 1, then terms of order epsilon, and then terms of higher orders. I could write those terms out, and we could do that. It just takes more math, more time to do. Okay. So now I take this and I plug it into each of these terms here. Okay, into the boundary conditions, and I write them out. So the linear terms, these ones are straightforward, right? If I take the second derivative of this, I'm just going to get that times the second derivative, right? If I take the first derivative, same thing. The only one that's a little complicated is the phi squared. So phi squared, I have to do by writing this and multiplying out all the terms. So I'm going to have phi 0 plus epsilon phi 1 plus order epsilon squared multiplied by phi 0 plus epsilon phi 1 plus order epsilon squared. Okay, this is just algebra, so I'm gonna get E naught squared plus, and I'm gonna get two of these, one on the insides and one on the outside. So 2 epsilon E naught 1 plus, and then when I multiply the phi1 by the other phi1, there's 2 epsilons. So I get an epsilon squared, and I don't care about things epsilon squared or higher, so I can just say order epsilon squared. Okay. And now I just take this and plug it into this equation here and turn the crank a little bit. So let's do that. Epsilon d2 phi 0 dx squared plus another epsilon d2 phi 1 dx squared plus higher order terms. Actually, I'll just save that till the end. Okay. Plus 1 over alpha plus epsilon over alpha d1 dx squared. Come down another line. Oh, I should have closed that parentheses, right? Because there's an epsilon multiplying with that guy, but there's no epsilon on that one. Okay, and then here I'm going to have minus the phi squared, which is what I just read. Phi naught squared minus 2 epsilon phi 0 phi 1, all that. And then that, now I can add my higher order terms plus order epsilon squared is equal to 0. Does that make sense? So then the last thing that I do is I can also apply this to the boundary conditions. So the boundary conditions are really straightforward. You just take and evaluate this thing at 0. So you say, phi 0 at 0 plus epsilon phi1 at 0 is equal to 0. And phi 0 at 1 plus epsilon phi1 at 1 is equal to 1. And that's higher order terms I choose. I'm just gonna stop it. Yes.
And I think along one option we have dx squared.
Do I have what's first?
Squared.
Oh, that should be squared. You're right. That's just a simple. Thanks for catching. I got all excited with the second derivative. Just started going. Okay. So now, yes.
Do we have an epsilon squared term in the first line that we can get rid of?
Yes. Yeah. So what's going to happen? So in these perturbation problems, if you recall, when we write this, epsilon's arbitrary. So what we're allowed to do is write we're allowed to equate some of the terms to each other. So the terms that are at the same order are all equal if epsilon is allowed to vary, right? So what that means is that everything that has an epsilon in front, I can equate to all the other things, and everything that has nothing in front, I can equate. And so I'm going to get 2 sets of equations. So what I did was I have one equation here that I don't know how to solve. And the hope is that in the perturbation method, I'm going to write this as 2 equations that I do know how to solve. And then hopefully that'll give me some, approximation, right? And of course, this is only good insofar as these asymptotic methods are good, which is in the limit that epsilon is really small, right? So these become more and more accurate as epsilon is. Okay, so like Mark that just pointed this out, right? This one's going to be order epsilon squared. So that one's not going to go with anything because I'm neglecting epsilon squared. So let me write down the order epsilon to the 0 or the order 1 terms first. Okay, so there's none of these are order 1. I've got one right there. I have 1 over alpha phi 0 dx. And I've got one right there. Minus phi 0 squared equals 0. And I can do the same thing with the boundary conditions that I do here. So here I've got something order 1, here I have something order 1. So I have P0 at 0 equals 0. And the same thing down here, I have P0 at 1 is equal to 1. And then I can write down my next order epsilon 1. Now I go collect all the terms that have an epsilon in front. So that one, I'm going to get d2 p0 dx squared plus, I'm going to have that guy, 1 over alpha d p1 dx. And I'll have that one minus 2 p0 p1 equals 0. And I could have written epsilons in front of all of them and then divided by epsilon because it's equal to 0. So they all cancel, right? And they're all always going to cancel because I'm only collecting the terms that have that order. So even if it doesn't equal 0 or whatever, every term has to have that order for me to pick it. So they'll all cancel. Okay, and then when I write the boundary conditions, now I'm going to have P1 at 0 is equal to 0. Well, why is that? Over here, I have an epsilon here, and I don't have any epsilons over here. So P1 at 0 has to be 0. And the same thing for P1 at 1. It has to be 0. Okay, because there's no epsilons in front of here. Okay, so now I have 2 problems to solve. Okay, and if you remember from the regular perturbation methods, what happens is I can solve the P0 problem. This made my problem easier, right? Because what I said was this small term, so that made this go away. So that made my problem easier. So if I look at this, I can separate and integrate that guy, and I'll be able to do that. I don't even need to separate, right? I just need to, no, I do need to separate. Move it over, divide, do the integral. Okay. But there should be an alarm bell going off in your head. There's a problem. You see the problem? Stare at it for a second. Yeah, what do you think, Tyler?
The boundary condition of an epsilon. I'm wondering why the boundary condition P1 is not 1 divided by epsilon.
This one? You want to know why it's not that? Why that one's not
Yeah.
1 divided by epsilon?
I missed something there.
Okay, so here I'm like, let me say this. Up here, I'm collecting all the terms that have either an epsilon in front, an epsilon in front, an epsilon in front, or nothing, right? I'm doing the same thing here. So I collect terms that have nothing in front. So there's a plus 0 times epsilon right here. Does that make sense? So when I collect this guy, I also collect that guy. So I don't use the 1. I already used the 1 because the 1 is, order epsilon to the 0 in front, just like that one. Does that make sense?
Yeah, thanks. I missed that.
Yeah. Okay. So that's not the thing that's funky. There's something else funky. Look up here. Think about what you're going to do to solve that equation for a second. What's going to happen when you try to solve that? You integrate, right? You're going to get an expression and you're going to apply the boundary condition. What do you notice about applying the boundary conditions to the solution we're going to get? It's more simple probably than you think. How many boundary conditions do I have? 2. What's the order of the derivative? 1. It's just 1 derivative. Oh, right? When I put the epsilon here, I lost my second derivative term. So that's funky. What's going to happen? Like which boundary condition do I use? Is it broken? What happened? Okay, so this is characteristic of these singular perturbation problems, is that I have this problem here with these boundary conditions. Okay, so we're gonna keep that in the back of our mind for a minute. We're gonna just plow ahead, okay? Thinking about like formally doing this, just repeating the form of it. Okay, so order 1, okay, or e to the 0. Let's do the math. Actually, I'll skip doing the integral. You can do the integral. There's lots of math in this already. I'm just going to write the answer. Phi 0 is -1 over alpha x plus c naught, where c naught is some unknown constant. Okay. How do I get that? I get that by moving this over here, dividing by phi naught squared, and I do an integral of something to the -2. I get that something to -1. That's where I get that. Okay. So then the question is, I'm just going to leave the boundary condition. Let's say, I don't know what to do with it yet. I'm just going to leave it there. Ignore it and go on. Then I'm going to do order epsilon. Now order epsilon looks pretty similar. Okay, but notice that I already know phi 0. So I've lost the second derivative here too. I'm not solving for a second derivative. I'm only going to be solving for phi 1. Okay, so I need to know what that derivative is, by the way. So I need to know what, if I know that phi 0 is this, I need to know what d phi 0 dx is. And that's what negative, let's see, positive alpha over alpha x plus c naught squared. Do I need a 2? No, I don't need a 2, do I? That's right. Okay. And then the second derivative is equal to, now I'm going to get a -2, right? -2 alpha squared divided by alpha x plus c naught cubed. Okay. I take that thing and I'm going to solve for phi 1. So I have 1 over alpha d phi 1 dx. I put everything on the right hand side. I have a 2 times a phi 0, which is minus alpha x plus c naught, and then multiplied by phi 1. And then I'm going to move over this. I'm going to subtract that from both sides, and I'll have a plus 2 alpha squared by alpha x plus c naught cubed. Okay. And now this one is painful, okay, because this I can't separate and integrate. So I'm gonna have to use an integrating factor. Remember doing that? Okay. At the same time, I'll just tell you the answer. How long? I get the following. E1 of x is equal to -2 alpha squared, phi naught squared, natural log phi naught plus a new constant, which I'm going to call C1, 1. Okay, well, we're out of time. Pick it up on Monday. So you also have homework due Monday, which has some bits. And then you're gonna have a new homework, or you have a homework that's posted, but I'm gonna add a problem on perturbation theory on it. And that one is due, I think, the Wednesday after Thanksgiving. So we have that homework, and I'll have one more and then we'll be done. So we're going to finish up this boundary layer theory here, and then we're going to talk about applying them to heat, mass, and fluids and be done.
Dr. Shree,
Yes, Andrew.
what is the subscript of the phi inside of the natural log? Okay, thank you.